It's great to be here. It's been very strange working on a project for the last couple of years with people that I've never met. So I met people for the first time on Monday, and I'm very pleased to have moved past that phase. So yes, today I'd like to talk about briefly about our effort at Google to create a standard software implementation of an EC based on Zephyr OS. So firstly, what is an EC? Does anyone have a laptop? Okay, only 3 of you, all right. Well, yeah, if you've got a laptop, it probably has an EC in it. It can use it's just an embedded controller, maybe ARM-based, but it can use any architecture. So we use the term EC to mean this particular chip in a laptop. The EC controls various features of the laptop that make it work properly. So I'll mention those in a minute. It's separate from the main chip in the laptop, which we call the AP, or application processor. The AP and the EC collaborate to ensure that various functions work correctly. So the EC's physical size depends on the space constraints within the laptop. It has some special features, such as an LPC bus for talking to an Intel AP. But other than those, as I said, it is really just an embedded microcontroller. So let's look inside a typical laptop and see what pieces the EC controls. So this picture shows the major ones, although there are many minor ones as well. You can see that the EC is involved in just about everything the laptop does. So having a good EC implementation is very important for a successful laptop design. So let's dig into those in a little more detail. First, we have the battery. The EC controls whether the battery is charging when the laptop is plugged into power, or discharging when it is not. It monitors the battery's charge so that it knows when it is almost empty or almost full. The EC can also track the battery temperature and get a feel for the health of the battery. Next is the keyboard. The EC scans the keyboard many times a second, looking for keystrokes from the user. The keyboard is not just a bunch of switches, separate switches, it's actually arranged in a matrix in row by column. So it must scan each column individually and handle things like N-key rollover, where multiple keys are pressed at once. When the lid is closed without an external display connected, or when the laptop is not used for a long time, the EC can put itself to sleep, or put the laptop to sleep to save the battery. The EC must then monitor the lid, display connector, USB, and other things to detect when the user wants to use the laptop again. USB seems simple as a user, but if you've ever looked at its specifications, it's a complicated beast. A laptop may receive power from a connected charger, or it may provide power to a phone, or both. With USB power delivery, PD, there are multiple voltages, and a negotiation takes place between the two devices as to which provides power and how much. Power may disappear on a port at any time, requiring quick reactions to keep things running. And speaking of power, some APs need a particular sequence to be followed when powering up, with each voltage rail enabled in turn with suitable delays. The EC handles that too. There are also sensors connected to the EC to detect the lid angle, system temperature, and so on. There may even be an accelerometer, gyrometer, or a compass. These must be tracked so the EC knows the orientation of a convertible laptop and can deal with things like getting too warm by turning on the fan or telling the AP to slow down. And finally, we have the interface to the AP, the main CPU in the laptop. The EC receives instructions from the AP and reports the current state of all the above items so that the main operating system, such as Chrome OS or Windows, and this results in a little low battery icon on the screen, or perhaps a message indicating that the laptop will shut down soon. So as I'm sure you can imagine, all of this takes a lot of software. It pretty much requires an RTOS with multiple tasks coordinating together. Overall, it's a surprisingly complex software system. So let's talk about our approach to Zephyr in Chrome OS. So first, a little bit of history. In the early days of Chrome OS, after shipping a few devices, we realized that the EC was a critical component of the laptop. So in true Google fashion, we built our own. It's called the Chrome OS EC, or ECOS for short. It was written in C, mostly by Randall Spangler, who is now actually a scuba instructor, but several others of us lent a hand. At first, it ran on an STM32 microcontroller containing an ARM Cortex-M3. It first shipped in 2012, 10 years ago, with Snow, the first ARM-based laptop. In 2013, it shipped with the Intel-based Link, also called the Chromebook Pixel. And since then, ECOS has served us very well for 10 years. It's fully open source, and many Googlers, ODMs, EC vendors, and other partners have, about 600 people in all, have grown this to around about 1 million lines of code. But while working on a Chromebook with Dell and Intel a few years ago, a few of us wondered if we could align better with the overall industry if we joined forces with a more externally focused project, as we've done successfully with Linux. I wrote a proposal to move to an RTOS for the EC. And as you can imagine, this generated a huge amount of internal discussion. Around a year later, there was enough alignment that I felt that we could usefully create a proof of concept. That went well. So I staffed up a small effort to get an existing laptop running with Zephyr OS instead of ECOS. After about 5 months of work, we were able to pass all the validation tests and had a fully functional EC based on Zephyr early last year. At that point, we made the decision to go ahead with using Zephyr in a bring-up project with an ARM-based design at first. We staffed the core team with one person to focus on each bring-up, to relieve anxiety on the bring-up teams. And now all developments are using Zephyr. The first devices with a Zephyr-based EC will ship later this year. But we have a lot of code in ECOS, and we need to redo that and submit it upstream to Zephyr. Work has started on this, but it's a big effort and it'll take a few more years. So why are we doing this? What does it mean to align better with the industry, and why should you get involved in this effort? Here are some reasons that motivated us. Firstly, we can have a unified code base. Now that sounds obvious, but having a shared code base allows complex problems to be solved collaboratively with multiple parties. It allows the implementation to be expanded and refined over time, and it allows chip vendors to write a driver once and use it to support multiple designs. Customers expect our products to work reliably, and with ever-increasing complexity, having a comprehensive and automated test environment is critical to achieving the desired product quality. This test environment is very expensive to build, so working together makes sense. By supporting Zephyr, EC vendors can, over time, bid for a wider range of design slots. On the other hand, OEMs can second-source ECs and use the same software. Perhaps more importantly, OEMs want to focus on their unique features and not spend money on the basics of getting a laptop to function. The EC implementation provides a solid base from which to add OEM-specific features such as diagnostics. So in short, Zephyr is a great collaboration vehicle for the EC while supporting differentiation as needed. So why did we choose Zephyr? In particular, why not FreeRTOS or one of the other options out there? Believe me, we had a good look around. Well, in my initial fiddling around, I found it technically attractive, and other Chrome OS engineers have since found the same. It has a powerful but straightforward configuration mechanism mentioned by the previous speaker with kconfig and device tree. It has a reasonable build system, and the code style is familiar, except perhaps there's just too many braces. And more than that, Zephyr has built a strong community with many industry players engaged. We've found it easy to encourage our EC partners such as Nuvoton, ITE and Microchip to port their code to Zephyr. And having more engagement improves quality and compatibility. For example, we expect to achieve better USB PD compliance with Zephyr. Releases are made, bugs are fixed, new proposals are discussed, and also you people are generally pretty nice. Finally, any project has to deal with technical disagreements, as well as competing designs and implementations. So we have seen how this works within the Zephyr community, and we're confident that Zephyr's governance can cope with these challenges as they come up. So what will the EC implementation look like on Zephyr? We imagine enabling it with a simple kconfig option, followed by turning on various other options for the extra features and drivers in use in the design. With the full USB-C stack, it needs about 0.5 mega flash and 64K of RAM. But for simpler applications, sizes will be smaller. We expect the tests to be automated and run quickly without needing real hardware. We'll leave the testing of the microcontroller drivers, such as the UART and I2C, to the microcontroller vendor. So we plan to have a high degree of code coverage. It's currently at 60% and rising, so that development can proceed confidently without constant breakages. And when we find a bug in our hardware-based tests or in the field, we can emulate those conditions and add a new regression test to avoid it happening again. Zephyr's app mechanism allows other applications to run for things that may not make sense to add to the Zephyr project itself, such as system-specific diagnostics. So that's the overview. It's obviously very high level, but I hope it's given you a taste of what we're trying to do. If you'd like to learn more, there are some talks today and tomorrow from members of our team, all of whom have contributed over 100 CLs to the ECOS code base. I'll just say that there's been a few changes, so some of these are check the schedule rather than just going on what I'm saying here. But this is what it is when I last looked. For a high-level technical overview, see Keith's talk, which is in a few hours. Keith is leading our Zephyr effort across all SoCs that Chrome OS targets. I think Keith might be here. Yeah, there you go. Hi, Keith. So for more details on the USB-C stack, Diana is doing a talk. I think it's scheduled tomorrow. Diana is the second largest contributor to the ECOS code base. For a more practical view of USB-C running on a real STM32, Sam has a talk. He's been focused on the tricky problem of upstreaming our USB-C stack. I'm not too sure when that's scheduled. It's become virtual. And if you want to know more about our test strategy and how we plan to support complex sensor arrangements, see Yuval's session. So Yuval is leading a team of about 6 engineers on our emulator and test effort. And there's also a little puzzle here for those of you not from Europe to decode the 24-hour clock. Can't tell if you're confused or not. I hope you'll find this of interest. Several members of our team will be at the conference today and tomorrow if you'd like to talk about it. So if an industry standard EC is relevant to you or your organisation, please get involved. Thank you.